Welcome to CSE132C. In this lecture, we will be discussing the topic of external sorting. An outline for this lecture, we will start with an overview of why external sorting is needed and what it is, and do a warm-up for how can we achieve external sorting using a toy example. Then we will generalize to what is called a multi-way external merge sort, or EMS, that is widely used in relational DBMSs and other large-scale data management systems. And lastly, we will talk about the relationship between EMS and B+3 indexes. Let's start with the overview. So in SQL, we have the order by clause. Now, the order by clause is typically used for ranking query results or for presentational purposes. And that is where sorting was originally kind of motivated. Later on, we'll see that external sorting is actually useful for many other applications within an RDBMS as well. For example, in a B+3 index, if you want to load the data from a file, then the process is called bulk loading, and external merge sort is used there, like we saw in the indexing topic. And later on, we will also talk about operator implementations and project, join, set operations, group by aggregate, many other relational operations when applied to large-scale data, larger than memory data, they implicitly can use sorting as well. But in your data structures and algorithms class, you must have studied sorting, like bubble sort and quick sort and so on. It's a well-known thing. So why are we talking about sorting in a database systems class? The difference is basically the scale. In the database, the file that stores the relation that you want to sort may not fit in your random access memory. Okay, so recollect that relational database systems were designed for secondary storage-aware access. Just like we saw with the index structures, everything is assumed to be paged and laid out on disk. And now you have to optimize for access to RAM to reduce I/O cost. Otherwise, it'll lead to thrashing. Okay, so this is where we call this external sorting as against internal sorting, wherein the entire data that you want to sort fits in DRAM. Okay, so whatever you studied in your algorithms and data structures class will be called internal sorting. And now we will talk about how to make one of those algorithms secondary storage aware. As an overview, here's our precise goal. We are given a relation R with, say, n pages, assumed to be on disk. We're given a sort key A, which is the order by clause attributes, for example. And then we have m buffer memory pages, buffer pool. So that's typically much, much less than n. Now, if it is not less than n, then you can just read the file and sort it in memory. Then we want to sort R on A to get a new temporary sorted file, R prime. The basic idea is that we need a sorting algorithm that is aware of disk IOs and optimizes for that. What are our desiderata for this external sorting procedure? One, obviously, we need high efficiency. We want to have very low I/O cost, even for very large n's. Okay, so recollect that n's for real-world relational databases, the sizes of certain files can even go into petabytes. So n can be in billions. We want to use sequential IOs as much as possible rather than random IOs. Again, notice that majority of the world's business critical data sits on magnetic hard disks, and the random sequential dichotomy is very important. Last, we also want to exploit systems capabilities like direct memory access, or DMA, to interleave IOs and computations, basically have parallelism between the two when possible. And of course, we also do not want to ignore computation costs or CPU costs, because at the end of the day, the wall clock runtime is what matters, and that is a function of both IO cost and CPU cost. In the majority of cases in database computations, IO cost often dominates, but we also should not ignore CPU costs. Notice that even though we are talking about relational database systems, this external sorting procedure that's IO aware is also a key part of the implementation of data flow systems, or the so-called big data systems like MapReduce and Hadoop, as well as Spark and other recent data flow systems. Okay, so understanding external sorting can be useful for these other systems as well. Okay, so let's start with a warm-up. The algorithm that is used in external sort is the merge sort. Okay, so recollect that internal sorting, the theoretical lower bound puts us at order n log n, and merge sort achieves that lower bound of n log n. Merge sort also happens to be very amenable to make it IO aware. So that's sort of what we will use. There are two phases for an external merge sort phase and merge phase. In the sort phase, the basic idea is as follows. We have the relation as a file on disk. We read each page of it into buffer memory, one page at a time, and then we do an internal sort for the records within that page in memory. For the internal sort, we can use any popular fast sorting algorithm from your algorithms class, example, a quicksort. Now we get a temporary sorted page, we write that back to disk. This sorted page is a seed for what is called a sorted run. And then this sorted run will keep growing larger and larger until the entire file gets sorted. Okay, now comes the merge phase. Now the merge phase is an iterative phase, so there will be multiple passes. And here in the merge phase, the basic idea of the two-way EMS, which is a toy procedure, is you read two runs into memory from this. You merge these two runs on the fly using the merge procedure in the merge sort. Okay, so where you keep pointers between two runs and then you advance the pointers. Now you get a merged run, which is double the length of the input read runs. Okay, so it's kind of the sizes of the two runs that you read put together. And then you write that out to disk. And then the second pass for the merge phase arises where you read those two runs and you keep going on. So you'll see an animation shortly. You keep recursing until the entire file becomes a sorted run. So notice that sort phase is just one pass of read and write. Merge phase is typically multi-pass. Okay, here's an illustration, a toy file with, say, these are the sort key values slotted into pages, 3, 4, 6, 2, all the way to some number of pages. In the first pass 0, which is the sort phase, you read each page one at a time into memory and then use internal sorting on those pages. Okay, so 3, 4 is sorted 3, 4, it's already sorted. 6, 2 is sorted increasing, say 2, 6. 9, 4 becomes 4, 9, and so on. You've written that out to disk. Now you basically need to read those for the first pass of the merge phase. Okay, so notice that you're reading in the page 3, 4 and the page 2, 6. You're merging them to create a sorted run of 2 pages, and therefore you get 2, 3, 4, 6. Similarly, the next pair, and then the next pair, and so on. Okay, so now you have read in 2 pages from 1 length runs, and you have produced a 2 length run as output. Now, if your number of pages in the input file is not a power of 2, you can have a dummy or virtual page that you imagine to exist, and then you can produce runs, and the last run may not be the same length as the other runs. Next pass of the merge phase begins, you read the 2 length runs, and then you output 4 length runs. So notice how 2, 3, 4, 6 merges with 4, 7, 8, 9, and then you get this sorted order of 2, 3, 4, 4, 6, 7, 8, 9. And so on. And then you keep recursing until you produce this 8-page run. Virtually, this last page is virtual, so there's only 7 pages, and that is basically the entire file. Okay, so now you have sorted the entire file in 3 merge passes. Okay, so the whole file is sorted. What is the total number of passes in general? The sort phase is 1 read and 1 write. So a pass is considered 1 read of the file and 1 write of the file. So the sort phase requires 1 pass. The merge phase, given n input file pages, in general, for this two-way external merge sort, requires log n to the base 2. And you take the ceiling of that. Notice again that each pass does 1 read and 1 write of every page corresponding to the file or a temporary file. Therefore, the number of page IOs per pass is n plus n, which is 2n. And so the overall IO cost of two-way EMS is IO cost per pass, which is 2n, times number of passes, which is 1 plus log n to the base 2. Okay, so that is the formula. We will keep revisiting this formula as we modify the EMS procedure with different optimizations. In this particular example, we have n equals 7. That's the total number of pages in the input file. And so what is the number of passes? It's 1 plus log 7 to the base 2. Okay, so what is log 7 to the base 2? You would basically get 3. Okay, so that's the ceiling of that. Notice that you do not need to compute the exact logarithm. You only need the ceiling. And therefore, you just need to get the next higher power of 2. And therefore, the total I/O cost here is 2 times 7 times 1 plus 3, which becomes 56. Now, for the rest of the topic's discussion, we're going to talk about how do we take this toy algorithm, the two-way external merge sort, and reduce this I/O cost further. Okay, so right now we have 56 page I/Os for this sort. How can we dramatically reduce that? This is where we're going to talk about the real procedure that's implemented in RDBMS called the multi-way external merge sort. Now, the motivation for the multi-way external merge sort arises from an observation about the amount of buffer memory needed for the two-way EMS. Okay, so how many buffer pages does it actually use to execute its sort phase and to execute its merge phase? Think about that a little bit. Well, for the sort phase, you only need 2 buffer pages, buffer frames. 1 frame to read in a page from the file, 1 frame to write the output of the sorted page. For the merge phase, you can make do with just 3 buffer frames. You need 1 frame to read the first run, 1 frame to read the second run, and 1 frame to store the merged output as and when you fill it, you flush it to disk. So the two-way EMS effectively uses only 3 buffer frames. That is very low because in modern systems, the amount of buffer memory you have can run into dozens of gigabytes. Sometimes in enterprise class machines, you even have up to 1 terabyte of RAM. So clearly there's going to be a lot more pages than just 3 that can sit in buffer pool. And therefore the basic idea of multi-way EMS is to exploit more buffer pages, basically big B, which is the notation we use for the number of buffer frames assigned to the EMS process. It's not necessarily the size of the buffer pool. You might assign a fraction of the buffer pool to the EMS sort process. And so this is much, much greater than 3. And the basic idea is as follows. The sort phase, instead of reading 1 page at a time, we read B pages at a time. Okay, so notice that with this, if you read 1 page at a time, you might end up with a lot of random reads or maybe impede the throughput of the reads. But now when you're reading B pages at a time, you can exploit sequential read throughput. And that will dramatically reduce your wall clock runtime, even though the number of pages is actually still the same. So the sort phase, you still read all the pages of the file, and then you write out all the pages of the temporary sorted run. Okay, so you read B pages at a time, you write out sorted runs of length B. You have done the internal sort on those B pages. What is the number of sorted runs after the sort phase? Because the length of each run is B, the number of sorted runs is N over B, because you need to take the ceiling of that. Each run is of length B, not just 1, as we had in the toy algorithm that we call the two-way EMS. Notice that the last run might be less than B pages, depending on whether N is a power or N is a multiple of B or not. The I/O cost of the sort phase does not change. It's still 1 read of the whole file, 1 write of the whole file, so it's still 2N. The real dramatic difference in the multi-way EMS compared to the toy algorithm, the two-way EMS, is in the merge phase. In the two-way EMS, we merged only 2 sorted runs at a time. In the multi-way EMS, we exploit the larger buffer memory we have to merge B-1 sorted runs at a time. Okay, so that's why it's also called a B-1-way merge or a B-way merge, depending on how you count. And here's an illustration for that. In the middle, you have the box, which is your buffer pool. That's the section of the buffer pool assigned to your EMS process. So you have B buffer pages. B-1 is assigned to B-1 runs. And then you have 1 frame assigned to hold the pages of the output as and when you get them. So B-1 runs, you read the first page of each run into memory. You apply the merge process like in your regular internal sort, advance pointers on each of those B-1 sets of records based on the less than, greater than, equal to comparisons, copy the records onto the output page. As and when the output page fills up, you flush it to disk as the next sorted run. So overall, now you're exploiting the entire B pages assigned to you for the EMS. Because of this B-1 way merge, what changes is the fan in or the base of the logarithm for the number of passes in the merge phase. Previously, it was log n to the base 2, and then ceiling of that. But now, because the sort phase has reduced the number of runs to n over b, the argument to the logarithm is n over b, and ceiling of that. But more importantly, the base of the logarithm goes up from 2 to b minus 1. Because you're merging b minus 1 runs into a single run, you are now exponentially better. Okay, let's look at the overall multi-way EMS IO cost. The overall number of passes in general is this expression over here, 1 plus log of n over b to the base b minus 1, because you put the appropriate ceilings. The 1 is for the sort phase, and the log n over b over to the base b minus 1 is for the merge phase. The IO cost per pass is still 2n, and therefore this is the general expression for the overall EMS IO cost with the multi-way merge. As an example, let's consider sorting a file with 100 million records. Let's say the length of each record is half a kilobyte, and let's say the page size is 8 kilobytes. And you're given the number of buffer pages for EMS that you can use is 1,000. So that's the number of frames you were assigned by the RDBMS for buffer usage. First, you need to calculate n, which is the number of pages. Okay, so the number of pages is 100 million times half a kilobyte divided by 8 kilobytes, which is 6.25 million pages. And therefore, the total cost of EMS that we've talked about, the multi-way merge EMS, is 2 times 6.25 million times 1 plus log 6250 base 999. Okay, 6250 is n over b. B is 1,000, n is 6.25 million, and therefore n over b is 6.25 thousand. The base of the logarithm is b minus 1, so that's 999. Now, this expression might scare you. You're going to wonder, how are we going to compute this logarithm? Well, for this edition of the course, of course, you're allowed to use calculators, so not a big deal. But even in the other editions, in the physical class editions, I would not allow students to use calculators because you do not need calculators. You can just estimate the ceiling of the logarithm without having to calculate the logarithm. You just need the power of 999 that is above 6250 or equal to that. And clearly 999 to the 1 is less than 6250, 999 to the 2 is greater than 6250, and therefore that expression is exactly 2. Okay, so the overall cost is 2 times 6.25 million times 1 plus 2, which is 37.5 million page IOs.